In this animation we answer one of the most important questions in linear algebra. Why do we set the determinant of a minus lambda I equal to 0 when we solve a differential equation? We will derive everything from scratch, step by step, so that every formula makes complete logical sense. Step 1. We start with a general linear ODE. By introducing state variables y1 and y2, any second-order ODE can be written as a first-order matrix system. Y prime equals A times Y, where A is the companion matrix of the coefficients. In fact, any nth order ODE can be written this way with an n by n matrix A. This is our fundamental equation. Everything flows from it. Step 2. How do we even start solving y prime equals AY? We use a powerful idea from scalar ODEs. The scalar equation y prime equals AY has solution y equals CE to the et. So for the matrix equation we try the same exponential form. Y of t equals e to the lambda t times v. Here lambda is an unknown scalar and v is an unknown constant vector. This educated guess, called an ansatz, is the key that unlocks everything. Step 3. Now we substitute the ansatz into the ODE. The left-hand side y prime is the derivative of e to the lambda t times v, which by the chain rule is lambda times e to the lambda t times v. The right-hand side is a times y, which is e to the lambda t times av. Setting them equal gives us lambda e to the lambda t versus equals e to the lambda ta versus. Step 4. Here is a crucial observation. E to the lambda t is never 0 for any real value of t. Therefore we can safely divide both sides by e to the lambda t. And it cancels completely. We are left with A versus equals lambda v. This is the fundamental eigenvalue equation. It says that multiplying vector v by matrix A is the same as simply scaling v by the scalar lambda. Step 5. We rearrange the eigenvalue equation algebraically. First, subtract lambda versus from both sides to get 0 on the right. Then write lambda versus as lambda IV, inserting the identity matrix, so that v can be factored out. The result is a minus lambda I, all times v, equals 0. This is a homogeneous linear system in the unknown vector v. Step 6. This is the heart of everything. We have the system a minus lambda I times versus equals 0. We need a non-zero vector v. Because versus equals 0 is the trivial solution and gives us nothing useful. Case 1. If the matrix M is invertible, we can multiply both sides by M inverse. And we get only versus equals 0. Useless. Case 2. If M is not invertible, the system has infinitely many solutions. And non-zero solutions exist. That is what we want. From linear algebra, a matrix is not invertible if and only if its determinant is 0. Therefore we must set determinant of a minus lambda I equal to 0. This is not arbitrary. It is the precise condition for non-trivial solutions. Step 7. Geometric intuition. The determinant measures how a matrix scales volume. If the determinant is non-zero, the matrix is invertible. It stretches or rotates space while preserving area. But when the determinant is 0, the matrix collapses space to a lower dimension. A square becomes a line. A cube becomes a flat sheet. That collapsed direction is exactly the null space. And the non-zero vectors in the null space are our eigenvectors. Setting the determinant to 0 is asking, for which values of lambda does a minus lambda I collapse space? Step 8. Expanding the determinant of a minus lambda I produces a polynomial in lambda. The characteristic polynomial. For a 2 by 2 matrix it is a quadratic. Lambda squared minus the trace of A times lambda plus the determinant of A. equals 0. For an n by n matrix it is a degree n polynomial. And by the fundamental theorem of algebra it has exactly n roots. The eigenvalues, counted with multiplicity. Step 9. Once we have the eigenvalues, we find the eigenvectors. For each eigenvalue lambda k, form the matrix A minus lambda k times I, row reduce it, and solve the homogeneous system. There will always be at least one free variable. That is guaranteed because the determinant is 0. So the system is underdetermined. Setting the free variable to 1 gives us a concrete eigenvector. Remember, eigenvectors are not unique. Any non-zero scalar multiple of an eigenvector is also an eigenvector. Step 10. Each pair lambda k, vk gives a particular solution e to the lambda kt times vk. Because the ODE is linear, any linear combination of solutions is itself a solution. This is the superposition principle. The general solution is a sum over all n eigensolutions with arbitrary constants ck. The x component of y gives us the actual solution x of t. When the eigenvalues are distinct, we have n linearly independent eigenvectors that form a complete basis. So every initial condition can be satisfied. Step 11. Let us apply this to a concrete example. For the ODE x double prime plus 3x prime plus 2x equals 0. With x of 0 equals 2 and x prime of 0 equals minus 1. We already know the matrix, eigenvalues, and eigenvectors. The general solution is c1e to the minus t plus c2e to the minus 2t. Plugging in t equals 0 gives c1 plus c2 equals 2. Differentiating and plugging in t equals 0 gives minus c1 minus 2c2 equals minus 1. Solving this linear system gives c1 equals 3 and c2 equals minus 1. So the final answer is x of t equals 3e to the minus t minus e to the minus 2t. Here is the complete logical chain from first principles. We start with the matrix ODE. We try an exponential ansatz. We substitute and cancel the exponential. We get the eigenvalue equation A versus equals lambda v. We rearrange to a homogeneous system. We demand a non-zero solution. Non-zero solutions exist only when the determinant is 0. That gives the characteristic polynomial. Its roots are the eigenvalues. Back substituting gives the eigenvectors. Superposition builds the general solution. Initial conditions fix the constants. Every single step follows logically. Nothing is arbitrary. Thank you for watching.